Let's try.
What's up, fellas?
Boiling.
We're boiling some propane today. We're going to try and stop destroying your boilers. And I think one of the problems that's doing that is the heavy ends that's in the propane. So we're going to boil some propane and take a look at what's going on here and see what type of residue we get out of just this little small test here. So we're going to let that boil off, and we're going to examine the residue. And the reason why I want to talk about this residue is because remember what I said about flame impingement and the fuel causing a fluxing action. Do you see this residue in this oil? This is called heavy ends. And this material is not only clogging up the spuds on your burner, it's clogging up the vaporizer coils in your vaporizer. In addition to that, once the vaporizer coil becomes full with oil, you may be spraying a large amount of that oil out into the system. And when you get that oil on the hot metal, it cracks thermally, releasing hydrogen into the metal, causing hydrogen embrittlement. So we got to change it up. So it says right here that HD10 propane is not used in vehicle applications. Ask yourself, why is that? So what you guys want to be doing is getting the HD5 propane. Just make that one of the rules of running the truck, that you can't put HD10 propane in it because it's going to foul out the burners, it's going to bust the coils open, and it's going to clog up your vaporizer. I bet you that vaporizer is full of oil at this point. I've got a hunch that it might be. All right, fellas, what we've got here is a little diagram that I've drawn up to kind of show what can happen when you're pumping oils and waxes through a process heating tube. I did a lot of research into this. What we're going off of is the book I got this diagram from, and it tells you some of the reasons why cracking occurs. And in our particular case, we have longitudinal cracks, which are straight down the pipe, and hydrogen damage and long-term overheat are pretty much the two problems that we're encountering here. So this is essentially what happens inside the boiler tube when you have direct flame impingement. First of all, you get this outside layer of the tube gets red hot in some cases. Inside here, you get this oil layer begins to carburize and break down thermally. You have thermally cracked this oil from its chemical composition of C18 or C8H18 to carbon and steam, and some nascent hydrogen and oxygen. The nascent hydrogen is the worst. That's individual hydrogen atoms by themselves. But nonetheless, even the diatomic form of hydrogen migrates into the metal of the pipe and causes hydrogen embrittlement. And that's one of the reasons that a crack can be sustained. You may have a hot spot, something like that. Now, I assume that the guys who are running these things in the winter area are draining this thing completely when they're done using it, so we're not getting any freezing, but kind of a dumb statement. I know you guys are way ahead of the curve on that, I'm sure, but just had to bring it up. But in addition to the hydrogen, let's say we just had water in this process tube. The outside skin of this metal can get really hot on flame impingement, and a little bubble can form right here. And hot metal and steam, especially iron, react with each other corrosively. So that's a huge problem. So if you're at 171 degrees and you're under pressure, say 300 psi's, I guarantee you can get little micro bubbles of hydrogen or micro bubbles of steam on the lining of that tube. Kind of the way you see bubbles form on a pot of water when you're warming it up. They'll be very small, but they still allow that pitting action. In addition to that, because of the high pressure, sometimes those steam bubbles collapse. And when they do, that's called cavitation. And that can pit little divots into the metal every time that happens. The tube you guys showed me that had a crack in it had been chopped in half with an oxyacetylene torch, it appeared. That's not gonna do, fellas. We need to be very delicate about an inspection on one of these boilers. It needs to be chopped with a gas axe, or that's what we call a gas-powered chop saw. We need to be very careful inspecting these tubes. On the next one you find that has a break, we need to see if we've got any carbon burnt on here or any oil sludge buildup that would surely be burnt away by any oxyacetylene cutting. So use an angle grinder or something. Whatever you do, don't use a plasma cutter or a torch to do this inspection. We should probably corroborate that's what's going on, because if we do have this buildup in here, we can scrape that crap off there by circulating some sand with a cyclone separator or a hydrocyclone separator to get the sand out on the other end of the circuit. Use a Ventura on the beginning of the circuit, and we could just flush these pipes out, and that could increase the lifespan. In addition to that, you guys told me they're pumping acid through these pipes. We're probably going to want to tell them to stop doing that. This is an iron pipe. That is going to cause stress, corrosion, cracking, which is another thing that can lead to premature tube failure. So that's where we are with one of the reasons why these pipes are cracking. Flame impingement alone is not the main mode. It's this thermal cracking of the C8H18 oil or the paraffin wax, which has a very similar chemical composition that's passing through this and causing hydrogen molecule migration of nascent hydrogen and diatomic, which is very destructive to metal. It gets in between the metal lattices and just kind of stays there and messes up the magnetic attractions of the metal and can cause cracks to form. Another thing that happens when you overheat the skin of a boiler tube is you lose that magnetite protective layer. There's a crystalline structure of a specific type that we need to maintain that is changed when you heat this above, say, 900 degrees, which is inevitably happening if you have direct flame impingement. So, how do we get out of that? What we're looking at here is a burner array that I built for a steam car group. They're attempting to beat the land speed record of 161 miles per hour with a steam car. And their problem is very similar to yours. They needed a way to throw as much power into the smallest area that they could fit in this car as possible. So they have a very similar condition to what you guys have going on. And this is what I came up with for them. Now, fabrication and testing included, they were at about $5,600 on this project. The boiler and the pressure washer pump is on the way. I'm going to be doing some testing with that in about a month. But I just wanted to show this to you guys because it's real close to what you need, size-wise and everything. So we would be right about here. I might be able to do it for less because it's maybe a little bit less welding due to the circular shape and all the box ducting in that. But we would be somewhere in that ballpark. And that's just for the first build. The second one, I would know exactly how long it took, and I would be able to streamline the process. And in addition to that, we could build the top setup of this, or possibly the whole thing, out of silicon carbide. I have a manufacturer in China, and he manufactures all of my silicon carbide nozzles. That right there is a recrystallized silicon carbide nozzle, and this is just regular RE, or SIC, I mean. That's RESIC. That's a higher grade, far more expensive. But this right here was like $12, so it's far cheaper than the metal, and it would last indefinitely. The stainless steel, if you kept it just red hot, would last probably 10 years. If you get it yellow hot, you could be as low as 1,600 hours of operation. But we're not going to run them that hot. We're just going to be running them red hot. All right, fellas, so I did not finish the drawing just for the purpose of illustration. I just populated this one zone. So we would have maybe not this many of these burners, but they would probably run better if we broke them off into quadrants like that. And we would just have an air manifold and a propane manifold, and there would be no nozzle. It's just going to be direct plumbing to the elbow of the air intake of this burner. And what that would do is allow us to burn all the fuel in an area about 2 inches above this and all the way to the bottom of this combustion chamber. This thing, the top is going to glow orange hot, and it's going to kick a lot of thermal energy in that direction. In addition to that, the amount of air that's going to be passing through is going to increase the BTU throughput of the boiler coil exponentially compared to just an air aspirated system. I got a feeling we could use less fuel and get hotter water because of the efficiency increase. But I recommend for now that maybe we do that. We just build a retrofit burner that can slide into your guys' existing equipment, and we just give one a try and see if the coil life is increased due to the lack of flame impingement. But that's one of the things we kind of want to pin down, and I feel like the best place to start would be with the burner system on your truck. Because if we can't learn how to stop from blowing up coils, there's really not too much point in going any further until we do. I think this is a good start. So say we do this, we throw it on one of your trucks. If it does increase the performance, then we can work on me building a prototype that shows you guys how to build the rectangle coil boiler system. I did include some money in the metal for a frame that's not shown in this drawing. It would just be like a pair of steel skids with some structuring to them so that this thing doesn't turn into a sweet potato on us. The performance of this burner design would not diminish over time. We ain't going to have these clogs and stuff that we're seeing in these large diameter plumbings. It's just not going to happen. That's one of the benefits of using this larger diameter stuff is the reliability factor. You know, spuds, as you guys have seen, do clog and all that. And another reason why this is quadranted off is because of structural purposes. If I just had this one big open box, it would warp and wobble all over on us. So we want to avoid that happening. This will also be sitting on a frame once said and done as well to keep it from bending up on us. Because it'll turn into a potato chip if we're not careful.